Hi, this is Dane Quinn from the University of Akron, and today we'll analyze mechanisms. And we're going to start off with the simplest mechanism that I can think of, right? We've talked about vectors, we've talked about loop closure equations and how to define directions, and now we'll try to put it all together. But again, we'll start off with the simplest thing that I can think of, namely a truss, right? So here it is. It's a three-link member. It has 0 degrees of freedom, right? So this is static. It doesn't move at all. Theta 2 is set at a given value. Theta 3 is a given value. Everything is completely static here. So the problem is the following. If I know L1, that's the distance between these two pins, I know the length of L2, that second link, and I know its inclination. What I'd like to find is the length of the third link and the angle theta 3 that it makes with the ground. Right? So we'll start off and identify the loop closure equation, define directions, take components, end up with equations, and solve. So loop closure equation is where we always start with this. And it's the closed kinematic loop that we can identify that describes the constraints. So here, this closed kinematic loop will basically follow these links, right? So the vector from O2 to A plus the vector from A to O3 is equal to the vector from O2 to O3. So writing that out, we have R of A with respect to O2 plus R of O3 with respect to O2 is equal to R of A with, O3 with respect to O2. Right? So basically that's just writing out this vector equation that we've identified. So now we need to figure out what all these things are. Well, in order to do that, let's go and define directions that are associated with these three vectors. So we'll always start with the ground, I and J. And then let's define directions fixed in link 2. All right, so I'll go ahead and redraw I and J. And then I2 is along the length, and J2 is perpendicular. And we'll define the inclination as theta 2. Then, looking at this third link, again, we have I and J for reference. And this third link, we will define with the angle theta 3. And this is the I3 direction. And then, of course, J3 is perpendicular to that. So now, these three vectors reduce to L2 in the I2 direction. Right, that's this vector. Plus L3 in the I3 direction, right? That's this vector. And that's going to be equal to L1 in the I direction. So here's our loop closure equation. This is a vector equation. It's got two scalar components, and we'll identify those by taking the components in basically the horizontal, or the I direction, and the vertical direction, or the J direction. So in order to do that, we need to relate our coordinates, we need to relate our directions one to another. So we'll relate I2 and J2 as well as I3 and J3 back to the reference frame I and J. So here, looking at I2, we see that I2 is cosine of theta 2 in the I direction plus sine of theta 2 in the J direction. J2 is minus sine in the I direction plus cosine of theta 2 in the J direction. And then looking at the third frame of reference, I3 is cosine I, now minus sine theta 3 in the J direction. And J3 is equal to sine of theta 3 in the I direction plus cosine of theta 3 in the j direction. Now, you should be able to do this. If anything is sort of puzzling you, maybe pause the video, go back and work these out on your own, and make sure that you can express I2 and J2 in terms of I and J like this, and the same for I3 and J3. In general, as you're going through these video lectures, feel free to pause whenever you need to, and maybe take a second and verify some of the work that I've done, or just kind of think about the things that I've said. That process of reflection will usually help you understand things better. Right, so here it is again, right? This is the mechanism that we have. It's our 0 degree of freedom truss and our loop closure equation. Notice that I have colored in red the things that we don't know. I know L2, I know I2, right, because I gave you this inclination at 60 degrees. Obviously, I know L1, I is horizontal, right? So I3 and L3 are the things that I am looking for. Right, so now the loop closure equation can be written in terms of I and J using those direction transformations that we defined. Right, so remember L2, I2 was cosine I plus sine J plus L3 cosine theta 3i, now minus sine of theta 3j, that was the transformation we found on the previous slide, equals L1i. So we want to take components. In the I direction, this reduces to L2 cosine plus L3 cosine of theta 3, and again I'm doing things that are unknown in red, equals L1. While in the j direction, we have L2 sine of theta 2 minus L3, and I said I was going to do that in red, L3 sine of theta 3 equals 0. So we have two scalar equations now. We have this scalar equation, which comes from the I direction, and we have a second scalar equation, which comes from the j direction. I'll remind you that in general, vector equations have two components and give rise to two scalar equations. So we need to solve these. Well, okay, I have two simultaneous equations. I'm going to solve one of these for one of the unknowns and then substitute it into the other. So I'll actually take this component in the j direction and I'll solve for L3. So here L3 is equal to L2 times sine of theta 2 divided by sine of theta 3. And you may recognize this as the law of sines. A lot of these trigonometric formulas fall out naturally from the things that we're doing here. So when I take this and I reintroduce it into this first equation, I get L2 cosine of theta 2 plus L3, which was L2 sine of theta 2 divided by sine of theta 3 times cosine of theta 3 equals L1. So this is an equation only on theta 3, right? So I can solve this. And in particular, when I do that, I find that tangent of theta 3, right? So tangent sine over cosine. I'll basically solve for tangent in this piece. And this is equal to L2 sine of theta 2 divided by L1 minus L2 cosine of theta 2. So this is just some algebra. And what we find is that theta 3 is equal to 21.79 degrees for the values given in this problem. So then finally, we need to go back and solve for L3. Well, I'll actually just go back to this equation that that was equivalent to the law of sines, and we'll see that L3 here is L2 sine of theta 2 divided by sine of theta 3. And now theta 3 is known, right? So I'll write that in again, the black ink. Because we just solved for it, right? Theta 3 is 21.79 degrees. Notice that we couldn't solve for L3 until we solved for theta 3. But in doing so, we find that this is 175 centimeters. So here we've solved for the third link, right? Theta 3 is 21.79 degrees, and L3 is 175 centimeters for the given values. Now, notice that this was kind of not the most fun thing in the world, right? And in particular, I ended up with two simultaneous equations. I will note, and this will be useful later, that this vector equation, I can write L3 as L1I minus L2I2. Well, why is this useful? Well, let me go back and make these red again because they're unknown. But here, everything on the left side is unknown. Everything on the right side, though, is known. Right? I know L1, I know L2, I know I2. So if I'd like to solve for L3, for example, maybe I can find a way to eliminate theta 3. Well, I can because the magnitude of the left-hand side is independent of the orientation, right? The magnitude is just L3, right? So if I take the magnitude of the left-hand side, that's going to be equal to the magnitude of the right-hand side. And magnitude here is denoted by these two horizontal bars. And I'll actually take the squared magnitude because that seems to be a little easier to calculate because the squared magnitude is the dot product of one side with itself. Right? So I have L3I3 dot L3I3 is equal to, well, the right-hand side dotted with itself. Again, if I want to find the square of the magnitude, I can just dot a vector with itself. Right, so the length of the left-hand side is equal to the length of the right-hand side. So this left-hand side is easy, right? Because this is just L3, I3. I3 is a unit vector, right? So we end up with L3 squared. And then the right-hand side, I can work this dot product out. And when I do, and again, this might be a good time to pause and do it for yourself, right? But I get L1 squared minus L1 L2 cosine of theta 2 plus L2 squared. And it turns out that this is actually the law of cosines. And, of course, if you plug these values in, you end up with 175 centimeters. So in this last bit, we have found a way to directly solve for L3 without worrying about theta 3. Essentially, we were a little bit clever and found a way to eliminate theta 3 when we went from the vector equation down to the scalar equation. Well, this idea, what we'll find, is going to be really useful for reducing the amount of algebra that goes along with these kinematic problems. And in a later lecture, right, I'll spend some time and I'll really show you how to figure out what to do to make that jump from a vector equation with two components and two unknowns, L3 and theta 3 in this case, down to a single equation with the unknown that you're interested in. So that's it for now. Again, this is our first mechanism, but the procedure that we went through here is the procedure that we'll really go through for all of the rest of the problems, right? So we'll identify loop closure equations, we'll define directions and vectors and coordinates, and then we'll try to go through and solve the resulting kinematic equations. So even though it's relatively simple, right, it still encompasses a lot of what we end up doing for all the problems in this class. That's it. Thanks a lot, and I'll say goodbye. My dogs were pretty good today, so no bloopers at the end. They're sleeping. Shh.